topic today is fatigue, but this time it's by fluctuating stresses. Fluctuating stress. Now, different people may have different definitions of fluctuating, so we are going to define it clearly. So when we talk about fluctuating stresses, we talk about in contrast with the completely reversed stress. Now you know this one very well. Now this fluctuating stress is in contrast with completely reversed stress. Let's recall what completely reversed stress was. If this is time and this is stress, then you had this sinusoidal. This is one cycle, and then you have another cycle. So here you have sigma max, sigma min, and because it is completely reversed, so whatever the value of sigma max, it is equal to the magnitude of sigma min. That is what is called completely reversed. Plus 25 minus 25 plus 80 minus 80. So if this is so, then obviously the mean stress here is 0. Mean will be simply sigma max plus sigma min over 2, just an average. And because these are equal, then you have this equal to 0. Now we didn't focus on this thing, we didn't even mention it, but it was implied there. All you had was sigma A. Now what is sigma A? If sigma m is mid-range stress or mean stress, then sigma A is the alternating component. This is also component, mid-range stress component or alternating component. Now this one, the definition will be sigma max minus sigma min over 2, and this will have some value. Now there we didn't focus on either this term or this term because there was just one stress component, and this was the stress component we are talking about. This is the amount of stress that we talked about acting on any body. For example, when we talked about the SN diagram, we are still in the completely reversed regime. So we talk about SN diagram, you will recall 3 distinct regimes. If it's steel, then it is 10 raised to the power 6. This one is 10 raised to the power 3. You have the low cycle fatigue here, and here you have the finite life. Here it is infinite life, and both of these, call this area, this is high cycle fatigue. So this is just a repetition. Now for 10 raised to the power 6 cycles onwards, if something lasts for 10 raised to the power 6, then we assume that it lasts forever. It is infinite life. Here you have SE, and this is the point where you have FSUT, and this point was SUT, ultimate tensile strength. Now this one was for a situation where by definition sigma m was 0. We may not have specifically used this term sigma m, but if you're talking about a bending beam, a rotating beam experiment, then by definition you have the same amount of maximum stress and the minimum stress. So you have this thing. So this sort of diagram is valid for this sort of system only. Now fluctuating stresses, they are different from completely reversed in that they will have, this is a zero line, zero stress line, this is again the stress axis, this is the time axis. Here sigma m will have a value, non-zero value. For example, let's assume this is that value. You have sigma max again, sigma min. Now apparently this is very apparent, sigma max is greater than sigma min in magnitude. Obviously the signs are different here, but you don't have the same value. So if that is the case, then if you use these expressions sigma m and sigma a, obviously you'll have some sort of value for sigma a here, and it's the same value here, sigma a. Similarly, you have the same, sigma a will always be same on both sides, and that is why when we talk about sigma a, we are talking, this is the value of sigma a. It could be positive, it could be negative. The same thing here, you'll have sigma and sigma a. So you reach on the one side, you reach this sigma m, that will be a value. Now in this case sigma m will not be equal to 0, and from there you go upward sigma and downward sigma a. So this is the definition of a fluctuating stress. The difference between these two being, here sigma m is equal to 0, here sigma m is not equal to 0. Now you can have different varieties of this load. For example, you can have, this was positive negative, let's call it positive negative, again fluctuating load. You could again have a situation where you have again this amplitude is constant, and you have positive positive. Similarly, you have this, the same, this line is sigma min, this line is sigma max, sigma m, and when you reach this, then you have sigma a, and you again have sigma a. This is again a fluctuating load because the mean stress is not equal to 0. You could have yet another variety. For example, let's draw it here. This is your zero line. Again, let's call this zero line, zero stress. And this is obviously, all of these are stress to time graphs. Now you have this situation where this is positive negative, you have positive positive. You could equally have something called a repeating load, which is nothing but again a fluctuating load, but here sigma min is equal to 0. This value sigma max will be there, and again you'll have some sigma m here and sigma a and sigma a. Again, this is another variety of the fluctuating load because sigma m is not equal to 0. And finally it could be something like this. This is the zero line, stress and time. You could also have this sort of a system. So let's call it, this one is positive 0. This system, again all the characteristics are the same, but in this case sigma max, sigma min, both are negative. So let's call this negative negative. But again you'll have a value of sigma m which is non-zero, and you have sigma a, and then you have sigma a will be above it or below it. So this is what we are going to study now. At least two things come to mind here, two questions, two confusions which are likely to rise at this point, and it is a good idea to handle those here, get rid of those so that we can move forward. The first one is I think we can, yes, here we can define the first one. The first confusion confusion or question that is likely to arise here is, you may have this sort of a system which has these high frequency ripples. This is a sinusoidal wave, all right, but there is something locally going on also. So the first thing is that this one can very simply, and experiments bear this out, that you'll have sinusoidal waves whenever there is some sort of a rotating machine, because things occur again and again. But if there are some other kinds of vibrations or some other kind of loading also going on at a different frequency, you may get this sort of a ripple effect. Now this sort of thing can very easily be handled by simply taking a simple sinusoidal wave, provided your sigma min and your sigma max are the same as these. So you just ignore these ripples, and experiments bear this out. So you won't be far off in your analysis if you do that. The second thing is similar in nature, but what if you have not a sinusoidal wave to start with? For example, this sort of a thing. This happens and then this happens. This happens and this happens. Now this is not a sinusoidal wave, but still there is a repetition going on. Whatever happens here in the first cycle again happens in the second cycle. There's a sigma max here and there's a sigma min here, which keeps on repeating here. So again, experiments confirm this, that you can simply these details don't matter much. What matters is you can simply convert it into a sinusoidal loading system, provided that you use the same values. The details don't matter much, because this is very easy to handle. As you'll see soon, it pays to convert this system into this system, and it will be accompanied by very little error, and experiments bear this out. So this thing shouldn't bother you anymore, because if you see this sort of a diagram, many people think that are we ever going to get this beautiful kind of a curve? Yes and no. If you get it, you can do this analysis, but even if you don't get it, if you get something like this or something like this, you can again convert it into this. So this is valid for fully reversed. This, at least the diagram, it appears to be a fully reversed case, but it is valid for fully reversed or fluctuating loads alike. Now we come to the fluctuating situation. The problem that we are facing here is that we have all the analysis tools with us available when we talk about the fully reversed load case. So here, if you want to design for a certain life, you can just read the stress here. If you want to design for a certain, if you have a certain stress in mind that you want to apply, then you can read the life. If you want to apply, if you want to design something for infinite regime, infinite life, then you can just take SE. But all this assumes that the reverse is the load is fully reversed. Now in this case, and I'm going to draw a general case here, general fluctuating case, and it will be valid for all sorts of varieties that we have seen. The main thing being that your sigma m is not equal to 0. That makes it a fluctuating case. So there will be a sigma max and there will be a sigma min. So I've just made this system, but it doesn't matter any kind of system as long as it has sigma m not equal to 0 qualifies. So just draw two cycles here. This is sigma max, this is sigma min, and let's define some things. Sigma m, you call mean, or you can also call it mid-range component. Sigma a, you're familiar with this, these are equal. Sigma a, this is the amplitude component. Now it's like we have seen already. It's very easy to see that sigma max and sigma m and sigma a are obtained by these expressions, because sigma m is mean stress. So by definition, average, you take average sigma max plus sigma min over 2. Similarly, sigma a, sigma max minus sigma min over 2. Only in this case, this will not be equal to 0. This was 0 for reverse case. Now, there are some other quantities also that quantify. Let's go. These are the variables that we need some variables to quantify the fluctuating load. If you get a non-fully reversed stress situation, you want to quantify it so that we can then analyze or design based on that. Now, the next thing is range of stress. Now, range of stress is nothing but sigma max minus sigma min. That is the range. Now, sigma max, you can very easily see what is sigma max in terms of these. Start from 0, sigma m plus sigma a. This is sigma max. Similarly, sigma min, that is sigma m minus sigma a. So if you use these two expressions, and you can get these obviously from the figure, and you can also use these expressions to get these. It's the same thing. Now, if you put these back here, sigma r turns out to be sigma m plus sigma a minus sigma m plus sigma a, and sigma r is equal to nothing but 2 sigma a. So this is another variable that quantifies. There are yet other things, for example, stress ratio. Stress ratio is nothing but sigma min over sigma max. And finally, another variable, if we're talking about quantifying this load situation, in real life you'll have some numbers to these, so you can always calculate these things. This is amplitude ratio, and this is sigma a over sigma m. Now these are just, we have just defined them, and it makes sense from the figure and as well as these formulas. Now if you look at all these variables that quantify or characterize a certain non-fully reversible, because not why this is fully reversible, non-fully reversible, because this mean stress is not equal to 0. If it was 0, then it would have been the same quantity above and below, but now sigma max and sigma min, they have different magnitude. So this is our system now. So all these quantify this. But if you look closely, sigma max, sigma m and sigma a, these are the fundamental. You can, if you have these two, although you can take any other as fundamental too, but if we take these two, if we have these two, then we can have all these. For example, if you have sigma m and sigma a, then obviously these are there. Range of stress, it is nothing but 2 sigma a. Again, you can calculate from here. stress ratio, sigma min or sigma max. Sigma min, sigma max, obviously they are given to you at the start, and you can just put in the values here, and you can just also get sigma min and sigma max from these also. Obviously you have calculated them, but if you have know these quantities, then you can have these also. Amplitude sigma or sigma, again, if you have this and this, then you, so actually if you get these two, then actually all other are just repetition. So we'll be using these two, using these almost exclusively. 99.9% of the time we'll be just dealing with these two quantities, because these already have all the information inside them. So this takes care of quantifying. Now this one thing that is often a source of error or confusion, and that is something called the steady or static stress. And you must make it clear at this point from the start that this is not the sigma m. This is not equal to sigma m. This is something else. I'll just take a minute to explain what it is. Let's say this is a plate and it is subjected to fluctuating load, plus minus f. Here also plus minus f. When I say fluctuating, by definition sigma m is not equal to 0, or in other words sigma max is not equal to the modulus of sigma min. So it means this system will be quantified by sigma a and sigma m, sigma a and sigma m. Your fully reversed situations, because sigma m was 0, so you only need to know sigma a, and that was the reversing stress, fully reversed stress that you plotted here. So that went without saying, but here in this case you need both, because these both are non-zero components now. Now what if, apart from this, in addition to this load which is applied, fluctuating load, you also have this some weight. Obviously this plate has some weight, so if the weight is also there, and it will always be there, then this weight is an example of steady load or steady stress, the stress caused by this load, this weight load. And why is that so? This delta, this plus minus f, this is completely quantified by sigma and sigma m. It depends on sigma a and sigma m only. It has nothing to, this weight has nothing whatsoever to do with fatigue. This causes fatigue, this combination. This is just a steady load that is applied once, that's all. So this is called a steady load. It is not sigma m, obviously it is not sigma a, it's not even sigma m. So this weight then has nothing to do with fatigue. So if it's a fatigue analysis that you are carrying out, then you will ignore it. Neglect. So this static stress is neglected. You don't consider it in fatigue analysis. So finally, in summary, what is our task now? The next task, now that we have quantified fluctuating stress and we know what is different about fluctuating stress than a fully reversed, completely reversed stress situation. So the task now is how to factor in the effect of sigma m, which is not equal to 0 in this case, on fatigue strength. So this is our task now, because again we call that this SN diagram, it is based on a completely reverse situation. So it's all very well to design for infinite life or for finite life or whatever, but that is only for a fully reversed case situation. Now if your case is not fully reversed but fluctuating, and now somebody asks you, or you are required to design something for infinite life or for finite life or what have you, then you cannot rely on SN diagram. So we need a framework for fluctuating stresses. Why SN diagram cannot be used directly? Obviously we'll use it indirectly, but why you cannot use that directly? Let's call this more accurate, because it is based on complete stress reversals. That's why. First of all, we need another diagram. SN diagram won't do, so another diagram is needed, and that is called the fatigue diagram, or alternatively, or the sigma m sigma a diagram. It should be very clear now. Before doing this fluctuating stresses, the only stress component was sigma m. Sigma a. Sigma m was 0, and so we didn't call it by sigma a by this name, but we knew what was happening there. Now that is why whenever we plotted this SN diagram, this was on this axis, it was always sigma a that was plotted. Sigma m was 0 always. Here obviously we need the effect of sigma m on the system, so it's very obvious that we need an axis for sigma m and we need an axis for sigma a, so that we can see what happens to the stress situation as we move along. Sigma m, how much sigma a can we apply on the body for infinite life, for example. So let's talk about infinite life first, and then we'll talk about finite life later on. The same thinking will be applied there too. Now, one thing for starters, it's very easy to know what should we plot for infinite life. What should we plot here? If sigma m is 0, this is the point, 0, how much sigma a can be applied for infinite life? This can directly be seen from the SN diagram. This SN diagram is for sigma m is equal to 0. So for infinite life you can apply stress of SE for infinite life. Okay, this is SE. We're talking about infinite life here. Okay, so for sigma m is equal to 0, this is the line for fully reversed stresses. You apply any stress in between here or even up to this point, it should behave. It should last forever, infinite. Now the challenge is, what happens to this stress? What can you apply? What kind of sigma a can you apply, the amplitude component, as sigma m increases? Obviously it should be lower than this one, because already you have you cannot afford now to apply the same amount here, so it should reduce, but by how much? For that, let's see the other extreme. What happens? What is the maximum sigma m that can be applied on a system? I think it's very obvious. Sigma m, if you apply SUT, which is the ultimate tensile strength, then the component breaks. There's no question of infinite life, or there's no question of applying an alternating component here after applying SUT. So the component breaks here. So this is the extreme load that can be applied. So these are the two. Sigma m maximum is SUT, minimum sigma m as far as the positive regime is concerned is 0. Obviously we can go to minus side also, but we'll look at that later on. So if this is the case, then one fatigue criterion for fully reversed loads is simply connecting this point to this point. And I'll explain this in detail. For example, if I'll just use two colors because I have at least two criterion here. If we connect these two lines, then this is the envelope. This is the border between infinite life. Any point that comes inside this diagram gives you infinite life, and all the points that go outside, they give you finite life. They fail because they break. Now this is called the modified Goodman line, this one. Now obviously this has to have some backing, some background in experiments, and there is. If you test a number of specimens with different sigma m values, then you'll have the breakages here, some breakages, they'll just keep on. Some will break here also, because in statistics there is no such thing as zero failure behind us underneath a certain line or something like that. This sort of situation is there. These are the points that not infinite life. They break, so there's no infinite life. Some of them will be below here also, but this line is the lower bound. Most of the points are above it, so you can say that this is a conservative estimate. You could have drawn it slightly above also, because if you recall, you can draw through the average, through the mean also, but this one is at the lower bound. Now is that all? I'm afraid there is one more thing. This diagram only tells you that if your combination of sigma and a sigma, for example, this is your sigma m and this is your sigma m, whatever the values will be, and we'll do some experiment and some problems also. If you plot it here, this is the maximum extreme where you can say that you have infinite life. This point here, no problem, this is infinite. But the moment something plots above this red line, it doesn't give you infinite life. So this line differentiates between infinite and finite life. So you would be tempted to think that any point that plots under this line should be okay. It is from the fatigue point of view. But please recall, there's another thing called yield. Now yielding is something that happens when your stress exceeds the yield strength of the material. So if this is the SUT, then the SY is around about 75%, so you can somewhere around here, SY, this is the yield strength. And you can also plot, this is 50%, and here this is your yield strength. Now if your sigma m is SY or greater, the moment it becomes SY, how much sigma A you can apply on the body? 0. There is no concept of infinite life here. It has already yielded here. Once something yields, fatigue is something that your stress is below the yield strength, but still after this many number of cycles it breaks. But if something yields, then that is another kind of failure. That is ductile failure. That is not fatigue failure at all. So if you have sigma m is equal to SY, then the amount of sigma A that you can put on the body for infinite life is basically 0. So that is why you plot the point here. What is the other extreme? If you have sigma m is equal to 0 here, and you apply sigma is equal to Sy, then again it yields. You don't need even 1 megapascal of sigma m if your sigma A is going to be equal to Sy. It will yield. So now you have two competing mechanisms. One mechanism is ductile failure. Just let me join these two again by straight line. This blue line, this is called the Langer line. This gives you ductile failure, yielding, and this is called, for very good reason, first cycle yielding. If this system is going to yield because of sigma m or sigma a combination, it's going to do that in the first cycle itself. It's not something like fatigue that keeps on accumulating over a period of time. After this many number of thousands of revolutions it will fail or something like that, or it won't fail for infinite life. If this will fail, it will fail on the first cycle. That is why it is called first cycle yielding. So now in summary, any point that is above this red line, if you plot your sigma and sigma m, we are going to calculate them. This gives you less than infinite life, or in other words, no infinite life. And any point that plots in this blue region, it gives you first cycle yielding. So in summary, the only safe region for you to locate your point in, because you are basically, first of all, there are two modes of failure here. One is fatigue failure, or no infinite life, because we are assuming that we are designing for infinite life here. Number two is first cycle. If this happens, then there is no question of infinite life again, because it yields in a ductile manner. Ductile failure. We have to avoid both these. So if we are to avoid both these mechanisms, then the only safe region, safe means no yielding and infinite life, both these, that region is so. For example, if your point locates somewhere here, there is no question of fatigue because already it has yielded. It has crossed this line, so you have yielded. If on the other hand something lands here, there is no concept of yielding because already you have failed this criterion of infinite life. The moment you cross this red line, you are in the finite life region, so you have failed this your goal. So you should be worried about fatigue failure if something falls here. If something falls here, you shouldn't be happy that there's no fatigue failure. It's still in, technically speaking, under the red line, so it should be have infinite life. There's no concept of infinite life. It will yield on the first cycle itself. I'll just make this clearer. The relevant portion for us then in this diagram is this. All our points for safety must lie inside this region. A point to clarify here is that why is this word modified appended to this Goodman line? What about Goodman line? Why is it Modified Goodman line. Why is it called modified Goodman line? It's one of the most famous lines, or the most famous words used in design, and you should make this very clear that the Goodman line, the original Goodman line, is not used anymore. There's a history of that line, and it dealt with sigma m and sigma a, but they were plotted quite differently, and that is not used anymore. So interested parties can look that up in literature. But that is why whenever you talk about modified Goodman line, actually this is the only line that is used now. So even if somebody says use the Goodman criterion, or use the Goodman line to design this or that, or analyze this or that based on the Goodman line, actually we are talking about the modified Goodman line. So Goodman line, modified Goodman line, these are the same things, because the original Goodman line, that is not used anymore. So this should be very clear. Now, one thing that we have not made clear, that is that sigma m could equally be negative. We have shown different situations, and one of these situations was this type of loading. So sigma m could be negative as visible, and it could have sigma max can be above it, sigma min is so far below it that sigma m is still negative. So there is a situation where sigma m could be negative, and what happens in that case? So let's see that also. And for that we need another figure, and this figure is called the augmented, another fancy word, the augmented Goodman diagram, or you can say the augmented modified Goodman diagram. Same thing, modified Goodman, for our purposes they are the same thing. But what does this augmented mean? This means that we have to introduce another region in this. So let's shift this graph that we have studied to the right, and let's include space for negative sigma also. So this is sigma m positive, this is sigma a. Now this is sigma m negative side. So let's make this again using the same scheme. This is SUT, this is SY, this SY should also be somewhere around here, SY, and SY should also be somewhere around here, minus SY, because yielding can occur on the positive side and the negative side, doesn't matter. Yielding is yielding. Tension, compression, most materials have the same strength, yield strength, in tension or compression. So if that happens, then you can just consider yielding on the opposite side also. We have already seen that if this was SUT, then half is SE, so half will be somewhere around here. So we have already seen that we joined this line, the modified Goodman line, to this. This is the Langer line. This is just a repetition of what we have done. So I'll use the same color scheme. Red for fatigue. This is irrelevant. Fatigue will occur first, so it will govern. If your point spills into this region, then already the fatigue has caused it to have life less than 10⁶. So there's no question of yielding or no yielding. So you already failed it here. Okay. But in this region, yielding occurs first. So in this region, if your point spills into this region here, then again, Goodman line will tell you that it has infinite life, but it would be misleading because it has already yielded. So here, this part is irrelevant. Now, what about the negative side? Now, experiments have shown that if all the failure points from the fatigue point of view, most of them occurred like something like this. Some may have occurred here also. But if your sigma m goes to the negative side, then Actually, fatigue strength is increased slightly. As sigma m increases on the negative side, you have you can apply more value of sigma a for infinite life, and that makes sense. Crack propagation, basically fatigue ultimately causes cracks, and then they proceed, they become bigger and bigger, and finally it breaks. So this whole thing, obviously it takes place because of fatigue, tension and compression, but tension is the driving force basically for, if you have a mean stress of zero, of negative applied there, it tends to close the cracks. It tends to, instead of opening them, it tends to close them. So fatigue strength is increased by mean stress in the negative region. But what we actually do is we don't rely on this increase to make our life easier, somewhat easier, and because it is on the safer side also, we just assume that the life, fatigue life, is unaffected by the negative mean stress. That is, if you have a mean stress in the negative, then you can apply the amplitude component of SE in this whole domain, and it should be all right. So we could have even increased this here, but we are using basically, we are making sure that it's a conservative design, but it makes life easier for us. So this is your negative region, but again you have to be careful. This yielding can occur on this side also. So we'll again use this. So our safe region now will be, if we consider all sorts of sigma m positive, sigma m negative, this region is our safe region now. Here is yielding already taking place. Here already you don't have infinite life. Here in reality you have, but because we are taking the conservative approach, here again it has failed because of fatigue, and in this region it has again yielded. So this diagram, this is called the augmented modified Goodman diagram, or augmented Goodman diagram, and this one should be able to take care of all your situations of stress, whether they are positive mean stress or negative mean stress or whatever the value of sigma a. Now one thing remains, and that is how to talk about finite life design, because here we have just talked about infinite life. That is, any point that lies outside it is infinite life, is finite life. Here it is finite life. So here is infinite life, here it is finite life. So finite life, we are designing for infinite life, so this is a failure point. These are failure points. So no point should lie above this red line. Okay, and similarly no point should lie outside this blue region also, because yielding will have taken place. But what if your concern was not of infinite life but for finite life? Well, that is, if you understood this part, then that is very easy, because if you consider this situation, how did we construct this diagram? Let's review this. You have this SN diagram, and I'm only going to draw this SN diagram from 10 raised to power 3 onwards. Because before this it is low cycle fatigue, and we are not focusing on low cycle fatigue here. Okay, so now you have at 10 raised to power 3, you have at 10 raised to power 6, your diagram is something like this. So here 10 raised to power 7, etc. Okay, now this point is for infinite life, this is SE. But if we talk about not infinite life but a life of 10 raised to power 5, this is N, this is S. So this stress, this strength. This is the strength of SF. Let's call it 10 raised to the power 5. What about 10 raised to the power 4? This is the fatigue strength of 10 raised to the power 4. And 10 raised to the power 3, obviously, you know what that is. That is F SUT, and you can again call it S at 10 raised to the power 3. But this point, if you want to design for this point, this is just the start of the high cycle fatigue and end of the low cycle fatigue. So you could go for a static analysis, or you could go for strain life method or something like that also, because this is just a border. So basically we are interested in the region after 10 raised to the power 3 and before 10 raised to the power 6. Okay, region after this and before this. Otherwise 10 raised to the power 6 and onwards it is SE. So how did we make this diagram from this figure? If you recall, we just did it. This diagram was made, or this is the augmented diagram, but if you just talk about the sigma m sigma a diagram, this is sigma m, this is sigma a. So how do you draw it? Very simple. This was your SUT. I'm talking about the Goodman line. This was your SUT and this was your SE. All you did was just talk about fatigue here. Just join these. So any point that lied outside, it was less than infinite life. Anything that point that fell inside this, it was finite life. But what if you are not interested in infinite life at all? Very simple. This is 10 raised to the power. This is SE. This SE came here directly. If you are interested in life of 10 raised to the power 5 cycles, simply take this one here, and this will be higher than this, obviously. If you are not interested in infinite life, then 10 raised to the power 5 cycles life, it should be higher than this. So you just join this. So anything that fell inside here, it had less than infinite life, but it is for 10 raised to the power 5 cycles, it is still safe. What if you are interested in a life of 10 raised to the power 4? No problem. Again, drop this. 10 raised to the power 4. This stress, let's call it SF. It should lie higher than this. Any point that fell in here, it failed as far as 10 raised to the power 5 cycles was concerned, but it is still safe as far as 10 raised to the power 4 cycles are concerned. And similarly for 10 raised to the power 3 cycles. And 10 raised to the power 3 cycles, actually very little application for this one, because this 10 raised to the power 3 SF. But again, I just mentioned this is on the borderline between low cycle and high cycle fatigue, so we don't want to work exactly here. But in this region, yes, it is valid. So now this diagram is for any life, including the infinite life. So you just pick your line. If you want to design something for 10 raised to the power 5, just this is your line to consider then. Otherwise, this is your line if you're talking about 10 raised to the power 4. This is 10 raised to the power 4, this is 10 raised to the power 5, and this is 10 raised to the power 3. So if this is the line you're talking about, you're only interested in 10 raised to the power 4 cycles. If your point lies here, it is safe. Safe means 10 raised to the power 4 cycles will be achieved and more. But if it falls here, then you have failed it. Fatigue will have taken place. But here again, you need to be very careful that you still have to draw the Langer line here too, because here again you have a danger of something that may be alright as far as fatigue is concerned. Langer line. For example, if some point lies here or here or here, depending on which life you want, from the fatigue point of view, they are all right, but they have already passed this blue line, so you have this failure already taken place. All these lines, these are again modified Goodman lines, depending on what kind of life you're talking about. Now, this is a very interesting point here, because you can use this process in reverse also. In reverse, I mean, here, if you want to design something or analyze something for a certain, you are basically interested in certain lifespan. So you just take that lifespan, you plot it here, then plot your sigma m, sigma a values, and if you decide whether that kind of life is achieved or not, and if it is achieved, what kind of factor of safety is there, and we'll do that in our next class. But this process is also used in reverse. For example, if you know your sigma m, sigma a, you plot them. Let's say the plot comes around here, this is plotted here. You are interested in infinite life basically, but obviously this lies outside this SE region, so there's no infinite life. So the next question then is, how many cycles will it withstand? So this is how we're talking about using it in reverse. If it had fallen inside here, you would have been interested in the factor of safety, and that factor of safety would have been this whole distance, because it can go till this point without going into the finite life region, but actually it only went this far. So this distance divided by this is your factor of safety, and you can reduce this factor of safety to 1 if it just plots right on this. So it's still, technically speaking, it is safe, but it is too close for comfort. So you only talk about factors of safety when you are inside the safe region, and it's in safe, by safety I mean SE, you're talking about infinite life. But if it plots here, now it's not a question of factor of safety, you have already exceeded the safe regime. Here the question is, okay, if not infinite life, then how much life will it endure? So the answer is very simple. You now plot this point, because these are all plotted from this point, so you just plot a line which passes through this point. Wherever it cuts, whatever SF you get here, you can read it. Okay, and we don't draw these diagrams to scale and then measure. Okay, we'll use some equations, and you'll be introduced to those equations. Very easy to use. So here we are just talking about what the process is. Okay, this is very important to know how you read these things, otherwise basically you'll be using equation. So you read this SF from here, and then you go back to your SN diagram. Okay, and then you plot that SF, because this SF is somewhere between SE and SF10.5, somewhere around here, wherever that is, you plot it there, and then this is your point, and then you go along to this point, and this is your number of cycles that it will withstand. So you can use it in the reverse direction also. And this SF that you read from this, it gives you the sigma reversed, that is, because ultimately you are going to use this SN curve, which is based on completely reversed. So this SF is, this system is not a completely reversed system. You have sigma m and sigma a, so it's a fluctuating system. But when you pass this line through this point and it touches this sigma a, then this sigma a is the equivalent completely reversed stress amplitude that has the same damage as your fluctuating system. So because it is equivalent completely reverse stress, so you are now entitled to go to your SN diagram, which is basically a completely reverse situation, and then read the end from there. So we'll just follow up on this by using concrete examples in the next class, and then we'll move on. Thank you very much.